Okay, sure. You can start, I guess. Your screen is huh.
Yeah. So we'll start today density ideas in NT. So at first I'll define what is the idea of density. So if I have to say in one line, it's kind of like size NT, but it's not exactly size NT. Like you look at the size only, but after a certain point, you want to compare two stuff and their sizes. So uh, take something like a polynomial p of x. For this, we consider only integer polynomials, which is like a n x to the power n minus 1 into x to the power n minus 1 a naught. So at the point of like infinite or very, very large, how will this polynomial behave? What will this be close to basically? Anyone? When like you make x sufficiently large, which thing will it like asymptotically grow as? Anyone? Okay. So see when you do like x value very, very large, px kind of is like a n x to the power n. The other terms, because they're like the power of x is less, so they don't matter much when we like go to a lot bigger x. So this is kind of the density idea. We don't look at the whole thing. We look at the thing that how much growth rate it has basically. So here px has like a polynomial growth rate, or so I can write px as something like O of x to the power n. Anyone has doubt till this point? Okay, I'll define another sign here. This is this sign. You have like probably seen it quite a lot. So we define like fx to be gx to be like asymptotically same. You can like define this sign in two ways. So one of the ways you can define is like fx by gx is bounded by two constants k1 and k2 for sufficiently large x. So basically, you don't take the constant factor in. Like p of x uh, is close to x to the power n. Like you don't take this a n, which is a constant factor. And another way you can define this is you also take the constant factor in. So you say at limit x power infinity, x tends to infinity, fx by gx is 1. So basically they're approaching to the same value when it goes to infinity. You can like use both the things, but if you use this, you have to be a little more careful because only the growth rate is not same. Even the growth rate is same, and it hits the same value at infinity. Okay, so
Aren't the
something
two
like
definitions different?
they are different, obviously. So if I take px to be a
Like
n
by
x
the
to the
second
power n,
definition, 2x and x won't have the same growth rate, asymptotic.
2x and x has the same growth rate, but we can't write this in, yeah.
Yeah.
that time. The second definition doesn't hold. But you will see on problems it don't matter much because it's like a constant factor, and we don't really care about constants when you're working on density. But you need to be a little more careful. Like I'll talk about something like weak P and T. Why do we like prove this thing? This is easily provable. But if you want to prove this thing, this is a lot more tougher to prove that they actually approach the same value. Okay. Let's talk about some function. So let's say something like 1 by 63 x squared log x plus 1 by, not 1 by, 5000 x squared plus 23 x log x plus 61. What is the O of this? What will the inner term be here?
X squared log x.
Yeah, because this is the largest term here. So after a point, the other terms don't matter much. We can like intuitively understand that. And if you want to write with this function, you should write 1 by 63 x squared log x. It is asymptotically same as. Okay. Wonderful. Now I'll straight go to a simple local problem. So you have to prove LCM of n comma n minus 1 comma n minus 2 dot till n minus d. The growth rate of CM is same as n to the power d plus 1. So they're not asymptotically same. So we are mostly using the first definition here. So you can also write this as O of n to the power d plus 1 basically. Can you try to prove this? That why both of these are growth rate is same. The LCM function and the
I think I have a proof.
sure.
So basically, you could calculate the LCM as a product of everything. Oh wait, no, I think I made a mistake. Sorry.
Yeah, you can take your time. Let's denote the LCM as S or something. So is there a defined way to calculate S?
Um, yeah, actually, I think we can do it. I mean, the GCD
Yeah.
of D2 terms has to be less than D. So you could bound that to D to the power of n, I guess. Like, yeah, I mean, you could basically bound that like to around D to the power of n plus 1. So what you could end up doing is you could take the product of everything and divide it by that. And you know it's like bounded between that value and I mean the product of everything and that divided by d to the power of n. I don't know if that works too.
I shall just write the first line you said. So I think you're trying to say we multiply everything n into n minus 1 till n minus d. It should be greater than equal to, I think, the sign. What will the sign be? Should be greater than equal to n minus d by what you can do is take each pairwise GCD. So what we do in like LCM of A comma B is like AB by GCD of A comma B. So here we are doing this for multiple terms. So the factor of inequality will be there. And you can take like each pairwise term. So you can write this as product of n minus I.
We can write ABC equals LCM of A comma LCM of BC. That's what you're doing, right?
Basically, yes.
Okay.
I should do I less than J. Yeah, basically I take the pairwise co-prime things and multiply all of those and like the product by this stuff. So the LCM has to be bigger than this because we're multiplying all the co-prime stuff and dividing it. So there won't be any factor, and it can happen that this stuff is actually like bigger because some term can be in two things, and so it will get cut out twice, not only one time. So we get this inequality. From here, can we simplify the lower term to be something more interesting, which will help us? What is the GCD? Okay, I should write the probably GCD here. The bracket means GCD. Okay. What is the GCD of n minus I n minus j?
It's probably bounded by I minus j. That's all you want.
It is bounded by n minus j, but n is becoming large and large.
Not n,
so-
I minus j. I minus j.
Exactly. So I consider j to be greater than I, so I'll write this to be GCD of j minus I, comma n minus j, which is less than equal to j minus I. So this product is bounded by product of n minus I goes to 0 to d by product of j goes to because d is a constant value, d is fixed, so this term will be fixed because we are multiplying to every number is constant and we are multiplying all the constant things, so it will be a constant. So we can just write this as like it will be greater than equal to product of I greater than 0 to d n minus I by some constant which has the growth rate of n to the power, because the numerator has growth rate of n to the power d plus 1 and we have the constant term which won't matter. So the growth rate will be similar as n to the power d plus 1. So of this thing. So we prove that S has growth rate greater than equal to n to the power d plus 1. And we can prove the other thing, other bound, which is also very easy because LCM should be less than equal to the whole product. So S less than equal to product of I equals to 0 to d n minus I, which has also growth rate of n to the power d plus 1. So we get that X must be have the growth rate of n to the power d plus 1. Okay. Is this clear?
Yeah.
Okay. I'll take it as a yes. Now, I'll introduce the prime number theorem. So, I think all of you guys know what is the prime number theorem. I'll just read the chat once before. Could you just show what we did? Sure. So we just understood what does the density idea mean. I took a polynomial function and said it is O of x to the power n because at infinity, the growth rate is same. Now, I defined this function in two ways. One is it is bounded by k1, k2. So I can write this as fx for this definition. I can write this as fx to be O of gx. And another definition I said was like they're asymptotically same, so they're approaching to the same value at infinity. Both of these are kind of same. They just don't. This thing has the constant factor, and this thing doesn't have the constant factor. Otherwise, both the things are not different. Sorry, 1 minute. Okay. And I took some example and I did this problem that LCM of the consecutive thing, d plus 1 consecutive thing is asymptotically same as n to the power d plus 1. Not asymptotically same as, the growth rate is same as. We don't take the constant factor in. So I'm using the first definition here. Okay. Is everything clear? A third.
Yes, thanks.
Okay. So I'll go to the prime number theorem. So I define this function pi of n. It says the number of primes less than or equal to n. Now there is a theorem which I only be able to prove sadly today. Is pi of n is n by log n. The proof for, if you want to use this definition, the proof is not that hard. Like it is pretty hard, but it's considerably easier than this proof. Because the thing is actually same, the constant also becomes 1 in this case. So their not only growth rate is same, also they're asymptotically same. Okay. Now try to prove this. You all know what is a Bertrand's postulate, right? So there must exist a prime between n and 2n for all natural numbers n greater than equal to 1. This is the Bertrand's postulate, which is proved. Now you guys can try to prove the generalization of Bertrand's postulate. So what I mean that primes belonging to n, comma, there exist primes such that it belongs to n, comma 1 plus k into n for sufficiently large n. So after a point, large n. So after a point, for any k greater than 0, I'll just write k belongs to R plus probably. We'll have a prime which exists between n and 1 plus k into n for sufficiently large n. Can you guys try to prove this using the prime number theorem? I'll just highlight this theorem. Okay. If you can understand the handwriting, so Do I need to say what are we trying to prove, or did you guys understand? Anyone?
Yeah, I think we got it.
Okay. By the way, if I open the meeting chat, can you also see the meeting chat or the screen only?
Only the screen.
Okay, that is good. Any ideas how to do this? So if you this is linear in some way, and we had prime to be like n by log n, so it's like less than linear. So can we use this? Let me see the chat. Question. Sure, I'll repeat the question. So you have to prove that for any k belongs to R plus, there exists a prime in the range n to 1 plus k n to 1 plus k into n for sufficiently large n. And n is natural number, of course. Okay. I'll just give the idea for this. If you see the difference here, so the prime must lie in the interval of n, and it is 1 plus k into n. So the length of this interval is like kn. So there must exist a prime in the interval which has like length kn. And we know that the like prime growth rate is n by log n. So pi of n is n by log n. So can you finish from here? Anyone?
They'd roughly be like k log n elements in that range that are primes.
But sorry, I did not get you.
There would be roughly k log n O of log n elements in that range that are prime.
Yeah.
Wait, no, actually no.
Wait.
No, it'd be
Why
pi.
O of
No, never mind. Maybe something like pi of 1 plus k times n minus pi of n.
I think I have an idea.
Yeah.
So like basically 1 plus k times n, like as you keep on, maybe like you could, when you graph it or something, like pi of n is like continuously increasing, like it has to be increasing. So if there were no such elements in between, then you would basically get like a straight line, right? I mean, like a straight line meaning like a horizontal line, right? But that's not true. So like I'm guessing that like it's like that's a
I
contradiction.
can see the idea, but I don't think that is the way to say it, right? Because why is like n specifically chosen? Like you have to use the growth rate somewhere, the specific growth rate of n by log n. Like if you see pi of n is just O of, yes, Nishant.
Can't we just like subtract like pi of 1 plus k into n minus pi of n? Like if you subtract it like that will give us the number of things in the range or whatever. And the thing is like it comes out to be what? Nk log n minus n log 1 plus k upon log squared n roughly. So like n log n dominates Cn is known. So like that it's non-zero after a while. It's like greater than or equal to 0 after a while. So
Yeah. So that is the idea. So this is, I need a prime to lie on Kn, which is O of n. Okay. And I know that there are like n by log n primes before the point n. And we know that O of n is greater than O of n by log n. So the gap has O of n, and there is like n by log n primes, and the gap is n. So there must be some prime, right? Because the gap is
But
more than the number of primes.
like n by log n is for 1 to n, not for any
Yeah.
gap of length n. Like primes like get more sparse, right? So the n by log n thing is for the range 1 to n, but does it hold for any range of length n? That's what I'm asking.
No, what you can do is like if you have a range of n, right? Say
Yeah.
1 to, I don't know, some k and then k plus n. So this
Yeah.
is like k plus n log of k plus n, right?
Right.
Minus k log of
Wait,
by
I think you
actually.
should, yeah, divide. Yeah.
Yeah. K plus n by log of k plus n minus k by log of k. See, the log term grows like much slower, right?
Yeah.
So, like basically the bottom two things are not much different. So you can basically cancel out n, k and kn, and the growth rate will be kind of same as n by log n. So this is actually O of n by log n.
Oh, okay. I see.
And see, there will be constant factors, but we don't need the constant factors. Like we can use the format definition of this thing, and we don't care about those constant factors that we'll get in the process.
Well,
So actually, any gap of length L will contain n by log n stuff. Like O of n by log n, there will be constant factors. For 1 to n, the constant factor is 1, but if you go more deep and deep, the constant factor will be low and low.
So just one question. So like basically, even if we did not know like what exactly this value would be like asymptotic to, like I mean pi of n is asymptotic to, like the fact that we know it's asymptotic to something would be enough to prove it, right?
Actually, no. We have to show pi of n is asymptotic to something which is less than n. So if pi of n was like O of n, so it's like a AP, in the real numbers, you can't prove it. Like this is not true. So it has to be asymptotically to something which is less than n in order to prove it.
Okay.
Do you see?
Yeah, yes, sir. But wouldn't that like if we knew that it was asymptotic to something, then it oh, I see, I see. Oh, got it, got it. Thank you, sir.
Now there is an interesting fact. You can try to use the prime number theorem to prove the Rother's theorem, which is actually not well known. That the nth prime, which is denoted as the Pn, is n log n. Asymptotically too. So you can take the constant factor as 1 now, C is 1. And you also have to prove the C is 1 here, basically. So you're using both the things. These are equivalent, but you have to prove it. Like, there is a bit of catch in the proof, but both the things are equivalent. This is kind of like a little bit of algebra, like not much NT. So you multiply stuff and see the growth rate. I write the prime number theorem again. So wait, let's not write pi of Pn. You can do it. But let me write pi of Pn only. So what is the pi of Pn? I just substituted n as Pn in the prime number theorem. Can't you subtract pi of n to pi of n minus 1? I mean, that will say that if n is a prime or not, but like pi of n is pi of n minus 1 in what we are doing, basically, for density purposes. Because the inner term is O of n only, so both the things are same. Actually, don't get you. If you can speak up, that will be nice. So pi of Pn is just n because it is the nth prime. It can be n minus 1, but we don't care here because we don't look for the constant things. It is Pn by log Pn. So if you just see, Pn is actually n log Pn. So we actually have to prove that, so this is equivalent to proving that log of Pn is same as log of Pn. Growth rate or asymptotically is not Pn, n. Yeah. And what we can do is just use a log here. So log of Pn is I should write in probably. It's asymptotically to log of Pn minus log of Pn. And if you see, we can divide both the sides by log of Pn, and this thing is small because log of Pn is some number, and log of that, like log of x by x, for x like large enough, that will tend to 0, so this thing will get cut, and log of n will be close to log of Pn. So we have proven this, and that implies P of n is asymptotically same to n log n. Okay. We can act like you are seeing we are doing the minus of log of Pn, right, which has some value. So actually log of Pn is a bit bigger than log of n, which you can see yourself too. And it has log of Pn asymptotically. So we are actually doing a lower version of it. So log of Pn becomes log of n is like a, even if they're asymptotically same at infinite, we are lowering the value in some way. So we can also say for any n, I think it is any n, for or for large enough n, Pn is actually greater than n of log of n log n, even if they're asymptotically same. This inequality is true. Okay.
Excuse me, sir.
Yeah.
So for the previous thing we did, like when we were trying to prove like the extended version of like Bertrand's postulate, like I didn't
Yes.
quite get why we're allowed to subtract both of those, because like technically like by the definition of like when like two like values are asymptotic, then like there should be like a lower bound for each of those, right? Like for a lower bound like constant type of thing. So like what if that when you subtract it using the lower bound for that k plus n by log of k plus n as the constant multiplied to that, and the higher bound multiplied to k by log of k, you get a negative value. Like I don't like, we haven't like dealt with that, right?
Like you are saying if we get something which is less than n by log n.
Like why are we allowed to subtract two values which are asymptotic?
Like because this is actually equal to, like, you can bound it by some c, you can introduce some c, and you can use like c1 c2 here, and some while c1 is the lower bound and c2 is the upper bound, and you can do like some other c3 c4, while c3 is the lower bound, c4 is the upper bound, and so you get actually upper bound and lower bound for both of this stuff, and c1 c2 doesn't matter. Like we can take the lower value, take the c2 out, so we'll have a constant factor on both the sides, but in the O of things we don't care about constant, right? So we can actually do this. And
But what if that constant factor ends up making it negative? Then that would be bad.
I mean, x by log x is like an increasing graph, right? So it can't be negative anytime for
Okay.
large enough x at least. Or we are dealing with only large enough stuff here, right? So
Oh, got it.
after a point, yeah.
Thank you, sir.
Yeah. Okay, now we are doing an actual question. You can still see the mirror screen, I hope, right? Anyone?
Yes.
Okay. Otherwise, there will be a bit of issue. But I'll just see a problem. The second problem that I will do. You guys can try to approach this, and I'll do the other question meantime. Try to prove this. 2 to the power n plus p of n equals to m factorial. P of n is like any polynomial in n. Okay. Try to prove this has only finitely many solutions in main time, or m and n and positive integers, while I'm pasting the question.
Could you just repeat the question again?
So the question says, for positive integers m and n, 2 to the power n plus p of n, where p of n is a polynomial, a integer polynomial in n, fixed integer polynomial, in n, and this equals m factorial. And you have to prove there is only finitely many solutions of the ordered pairs m, comma n, finitely many solutions to solves to ordered pairs or unordered, doesn't matter, m comma n. So I'm going to show that after a point, there will be no more solutions. For sufficiently large m comma n, there are no more solutions.
Okay, got it.
By the way, don't have to call me sir.
Okay.
If you want, we can actually try this problem first and then go to this problem. We have enough time to do the China problem. I'm not sure. Hopefully we can do it. Okay. So what type of contradictions are we looking in this problem? Is everybody okay with this problem first? Okay. This is problem
Yeah.
1, right? And this
I
is
think
problem 2.
V2 makes sense over here
Yeah, V2 makes sense.
because V2 of the left hand side will be small compared to the right hand side.
Mm-hmm. So if you intuitively see, the growth rate, the actual growth rate, will depend upon the 2 to the power n term, because O of 2 to the power n is bigger than O of Pn. For Pn can be any degree, but 2 to the power n will overcome P of n after a point.
Yeah.
But in some way, if you take V2, V2 of Pn will, V2 of m factorial will depend upon the V2 of Pn.
Yeah.
So can we get contradictions with using that? Yeah, that's a pretty good idea.
So like say Pn has degree d, we know that V2 of Pn is something like d log n, because it's bounded by an to the n times n to the d. So V2 of P of n is at most log 2 of P of n.
Okay, I'll just write those down.
Like V2 of anything is at most log 2 of it. So it's something like d times log n.
into an, but I'm not using like the definition. I will use the first definition to make my
It's
work
more of
easier.
plus log an,
Because
which is like negligible.
yeah, there will be like a lot of constants which we like neglect. Basically,
Wait, why
this
is
is not
it
asymptotic.
Can you explain this last thing?
Why is this true that logs approximately log to n?
It's not absolutely log to n. I'm saying it's the growth rate is same as log to n.
But that doesn't make sense.
Yeah,
Like,
why?
So Pn is like O of an n to the power d, right?
Yeah, that's right.
So
That's
V2
yeah.
of P n, if you take, this will be O of, uh, let me use this notation. So
See, like
an
for
will go
odd n,
outside, so we don't get an because that's a constant, and we'll have d log 2n, right?
d log 2.
No, but like the other
See, like
terms in the problem. Yeah.
for even n, it should probably be determined by the constant. Like,
See. Here we don't want to do any even odd stuff. We are just bounding it. Like, which thing? Like, there will be constant, a lot of constants that other terms will give. This will not be close to this. But the growth rate will be same as log 2n, if you can understand what I'm trying to say.
can't we say it will be like strictly less than or something? Like, same
Yeah,
doesn't seem correct. Like, log
like
2n
if
will be
n is
much larger,
even,
right?
yeah, and like if n is even and like the constant is odd, then the V2 will be zero. So like how do you
Yeah,
exactly?
I know. Like, I'm saying it's like, uh, it is less than equal to, like, V2 of Pn is less than equal to this thing, basically. Like at max, it can be d, the growth rate can be d log 2n, but n is like even and odd. But we don't do, like, we take the best case. We're taking the best case when it goes to the infinity, basically. Like
Uh,
at infinity, there is no even and odd type of thing, right?
But
but like in general, you can't. It's like not ethical to say V2 of P of n is approximately this, right?
No, it's more like bounded by this.
what about the
Yeah.
equality case of V2? Like, what if Pn has some high V2 for some n, and then this will fail, right?
No, but like we want to show that for high end there aren't solutions. So like this would help show that for higher end there aren't solutions. Because like, we have
Um,
finite solutions now. So like even if it holds for say up till 1 million and after 1 million there's nothing, and this helps in that proof, then we're done now.
um,
Is this
like
okay?
maybe I didn't get it still. What if V2 of Pn equals V2 of 2 to the n?
That can't happen
But
because
it's for large enough and it won't
then
happen.
Pn should be 2 to the power n, right? Like at least greater than or equal to 2 to the power n. But for large enough n, 2 to the power n is much bigger than any polynomial
Oh,
function it can ever be.
right, that makes sense.
But
Okay.
like,
Mm,
Yeah, go on.
never mind. Never.
Like what I'm just trying to say is that other constant term will have like will give something. So you can bound the other constant term to be like, say it's like some c n minus 1 to the power n to the power d minus 1. So you can also make this like n to the power d, join here, join the constant term. So after all the constant terms will get increased, but we don't care about the constant things.
okay, it
So
makes
V2 will
sense.
be bounded by it,
Right.
log 2n. It can't have like V2 of n. It will be bounded by log 2n, yeah. Some product into log 2n. So we can say that V2 of Pn is less than equal to k log 2n. Is this clear? Everybody. I'll highlight the question.
For some sufficiently large,
Yeah. I mean, if it is not sufficiently large, if it is small also, you can take the maximum for the small elements, and for the sufficiently large, take that k, take the maximum of that. So
Oh yeah.
even if it is small enough, you can get such a k, but the k will be probably higher.
I think V2 of m factorial is like around m. It's less than or equal to m. No, not less than or equal to, but it's
We want to use the other kind of inequalities. So if we do V2 of this thing, so V2 of Pn is V2 of m factorial. You guys can see it, right? This is the equality for large enough n. And what is V2 of m factorial? If you know the VP of n factorial thing, so it's like m minus s n minus spn by p minus 1. So it's m minus s2m. What is s2 of m? If we write m in binary, the sum of digits in the binary, and which is bounded by m minus log 2m. Okay. So we know that V2 of Pn m minus s2m is greater than, because s2m is less than log 2m, so it should be greater than.
Wait, is it log 2n or d log 2n in what you wrote? V2 of Pn less than equal to log 2n. On the left.
V
Here.
Oh, here.
Yeah, is it multiplied by d or no?
It is like I did a k here, right? I wrote the k here. So k is a constant.
Okay, okay, we don't care about that.
Yeah. Like there will be not d, like the n will also be there and other terms. So just take a bigger constant, like large bigger constant, which will doesn't matter. Because we don't care about constants here. So we have V2 of Pn to be greater than this. We also have V2 of Pn to be less than this. So we can say K of log 2n is greater than equal to m minus log 2m, right? Now try to prove the size thing. I should paste the. Is there any way to move this thing? I don't see a select option for some reason. Okay. I can't select probably. I'll do the things in down only. So 2 to the power n plus p of n is m factorial. This is the question we're doing right now. So what will be the size of m factorial? Which thing is bigger here? And
M
we'll take over.
factorial is bigger in general.
Not this, like out of 2 to the power n and p of n.
Or 2 to power n.
Yeah. So m factorial is greater than 2 to the power n. We can
So
say m to
from
the
this you
power
want
m
m
is.
like from this you
I'm
want
not.
m is much lesser than n, right?
No, we are getting a m is greater than n bound, and from here we're getting a m less than n bound. So we are
No,
getting two
it's
types
the
of bound.
opposite.
It's not opposite. Like we have m factorial greater than 2 to the power n. So we'll have something m greater than some things on in n greater than some things in n, and we here have some things in n greater than equal to some things in m, right? So we'll have two different types of bound.
Yeah, like I was saying, if m factorial is grows faster than 2 to the n and they have to be equal, that means m is
No,
much
just
lesser than
use
n.
this. Just use this 2 to the power n plus p of n. P of n is positive, right? So m factorial is greater than 2 to the power n.
Right. Okay. Yeah, makes sense.
Can you scroll up a bit, like just a bit?
Yeah. Is it
Okay.
fine?
Yeah, sure. Yeah.
And we can say m to the power m to be greater than m factorial. Because like it is 1 to m, and everything 1 you can change to m because m is greater than everything that is less than m. So m to the power m is greater than m factorial. And you take log. So m log m is greater than n log 2. m divided by log 2 of m greater than n. So we have two types of bound, m log 2m greater than n and k log 2n greater than equal to m minus log 2m. So see, here m and n is related because log 2 of m is like small. So some kind of way m and n are related. And here m and 2 to the power, like log 2 of n is related, not n is related. So we will have like problems. Do you see intuitively why we will have problems? Just do 2 to the power of this. So 2 to the power k greater than n. Here 2 to the power m by n. And here use like substitute the n here. So 2 to the power m by 2 to the power m by m greater than equal to 2 to the power k into m log 2m. But I'm changing the inequality sign, it feels. M log 2m. And this can't happen because 2 to the power m take the m to this side. So it's like m square log 2m, some constant, and 2 to the power m. So 2 to the power m is much, much bigger than this thing, where like for far enough m, and because k is a constant. So k doesn't matter, this is constant, and this is O of m square log m, and this is O of 2 to the power m. So this is much bigger. So we have a contradiction for large enough m. So if there is finitely many m, there will be finitely many n to the solutions. Is it fine? Any part of the solution you have doubt in, you can ask.
Could you just repeat the last part? The
Last part, yeah.
like from like k log base 2 of n is greater than or equal to that to like the next step and like just that one.
Oh, did you have a like problem in this line, right?
No, like after that,
Oh,
like
from
what we
here,
did after that.
from here or from here?
From like the first arrow, like the 2 to the power of k.
Oh, we just do it 2 to the power of the whole thing because a greater than equal to b implies 2 to the power a greater than equal to 2 to the power b if a and b are like greater than equal to 1. So
Okay, yeah.
So we just did 2 to the power k into 2 to the power log 2 of n, which is n. So 2 to the power k into n greater than equal to 2 to the power m by m. And from there, we substitute the value of n because we have the right inequality sign here. So instead of n, we did m log 2m. So we have a whole equation on m. So 2 to the power m should be less than 2 to the power k into m square log 2m, but that is not possible, which because of like size issues, m grows much faster than this.
Okay. Got it. Thank you.
Aritra,
Yeah.
wait, can you check what I wrote in the chat once? Is that like how we bounded the V2 of Pn? Like because V2 is less than or equal to log. Is that what we used?
Yeah, you can say that. But I think you need the small fact, which like this sign you are using is a same sign is a using is a issue because otherwise you also will have constant factors. So you have to
Yeah,
use
you
like
said
the
like not
O
a
of,
constant, right?
yeah.
Okay,
So that doesn't matter. Like basically this idea is what you're using. Yeah.
all right, thanks.
Do you want to do the China problem or this problem? But I'll introduce something before. So does everyone know what is Dirichlet's theorem here?
Yeah.
So for those who don't know, I'll just mention a theorem. In a AP, AN plus B, where AB are co-prime, A comma B is 1, we will have infinitely many prime numbers. Now it says that there is a weak dirichlet's theorem. Now there is a strong dirichlet's theorem which says that the densities are also even same. What I mean by that is, if you have AN plus B and AN plus C, B not equals to C, okay. So the number of primes you will find in AN plus B and number of primes you will find in AN plus C will be same, asymptotically same. They will be kind of equal. And B also A comma C is GCD of A comma C is 1. So like 5n plus 1, 5n plus 2, 5n plus 3, 5n plus 4. All the prime numbers there are, like 1 by 4 will be like 5n plus 1, 1 by 4 will be 5n plus 2, 1 by 4 will be 5n plus 3, 1 by 4 will be 5n plus 4. So if we define the function pi of EBX, which defines the number of primes, which is A mod B, number of primes, A mod B, which is less than equal to X, will be asymptotically same as 1 by Do you see why this is true? Because there are phi of B type of A's we can get. All the things are same, and total the density of prime is like n by log n. So the each density A mod B will be 1 by phi B in n log n. Like the constant factor will be 1 by phi B. So this is actually asymptotically same. Not only like the growth rate is same.
Could you repeat this part?
Yeah. So what I'm trying to say is, if there is like A mod B, A1 mod X and A2 mod X, the number of primes, which is A1 mod X, and number of primes, which is A2 mod X, will roughly be same. So all the things which are co-prime will roughly be same. So if we have like X to be very, very large, tending to infinity, A, B are constant, and we define the pi function like this. That number of primes A mod B, which is less than or equal to X, this thing will be asymptotically same as 1 by phi b n by log into n by log n. So n by log n, it is same, and the constant factor in this case will be 1 by phi b.
I have a doubt. Why are they approximately same? Like,
These are strong from Dirichlet, like I can't prove it. Like this is the theorem, I don't know the proof of. So the weak Dirichlet says there will be infinitely many primes, and the strong Dirichlet says that in every one of these APs, the density of primes will be same. And like this is not much used. Like I have also haven't seen a problem which uses this. If you guys see some problem in future, do let me know. Okay, now we can come to this problem. We can do this problem or the China TST. If this is A and the China TST is B, you can vote for the problem. Or I should write what is China TST. The China TST problem is one liner. I'll just say you have to prove that there exist infinitely many n belongs to n such that n square plus 1 is square free. So what does square free means? I think every one of you know, still I'll just say it. Square free means that there doesn't exist any prime p. Say a is x is square free, so there doesn't exist any prime p such that p square divides x. Okay, so this is the China TST, or we have this problem. Can I make a poll here? I don't think I can. Just vote A or B. Okay,
what
everyone
about
is writing B. Okay,
what?
sure.
Could you repeat the China TST problem again?
So there exist infinitely many n, infinitely many, such that n square plus 1 is square free. You have to prove that. And square free is prime, square does not divide n square plus 1.
Okay. Could we do this one?
Yeah, I think everyone is voting on this. So okay, let us do this. This is a bit overused problem, and this is like a kind of unknown problem. So you can like try this in home, and if you have any progress, take a screenshot right now. I'll like zoom on this. Take a screenshot in 10 seconds if you are done. Let me know. Okay, I hope all of you are done with the screenshot. Then we have like 20 minutes. I think that should be enough to finish. Give all the ideas you have in the problem. Like, can you think of a way? How can we prove that n square plus 1 is square free? What way should we go? Like, this seems so random. How can we do this? What happens if p square divides n square plus 1?
E is 1 mod 4.
Perfect.
And also
Why is
n
that? Yeah,
and also n square is only one of two values mod p.
exactly. Great
Wait,
ideas.
what did you say?
I'll explain. Bhairav can tell.
It's
So,
just saying either then if p square divides n square plus 1, then n has to be one of two only two values mod p,
Oh,
or
okay.
mod p squared in fact.
Right. Okay, that makes sense.
so he's saying n square plus 1 being 0 mod p
Oh,
square
because this has only two roots.
has two solutions. P1 mod 4 means like p greater than equal to 5. It can't be 2. Great.
So
Now,
wait, I'm thinking something like we can select n in the range of 1 to m for m to be decided later. And then we bound the size of the prime factors if it's not square free. And then with these bounds, we can say that for each prime factor in this bound, there are only a certain amount of n such that p divides that n squared plus 1. And then if we have some many things that are remaining, then we would be done. Something on those lines.
I see. So you want to bound n to some range m, and then
Yeah.
you want to like look at the prime factors of that.
Yeah.
I see. Let me think in that way if there is something. We don't have much time. Should I start revealing the solutions? I don't know. This is a good problem though. Okay, I'll give you two things. You can try to work on that. So let me define two things, and I will motivate the idea why we're defining this. AK, which just counts the number of values of k, the number of values of n, such that n square plus n square free, and n lies between k, 1 to k, and n square plus n square free.
Oh, it's like,
It's the number of count, like you're counting
yeah,
which
counting
things
function.
till
Okay.
k, counting function, yeah. So basically you want to say AK is not constant after a point, right? Because that's when you want to prove AK is like infinite. So it's a very motivated function to count. Another function we define is bk comma p. This function is when p square divides b square divides n square plus 1, and n lies between 1 to k. So for each prime, different prime, we'll have a different b k comma p. So it also depends on p. Do you see why did you introduce this function? How can you connect these two functions? Like they're connected in some way. You just have like a p extra here. So what do you have to do to remove this p? I'll just charge my laptop, one sec.
BK comma P is what again? It's the number of like n between 1 and k such that p squared divides n squared plus 1, right?
Sorry, what did you tell? I was a little bit out.
No, nothing. I just wanted to confirm like bk comma p is just the number of n between 1 and k such that p squared divides n squared plus 1, right? Okay.
Yeah, exactly. So like if p changes, bk comma p also changes. So it depends on both p and k. So both the things are kind of counting function. Okay, there are ideas in chat, I think. Arthur, your idea is correct actually, but you have to formalize those things. Like the idea is actually not hard for this problem, but you need to actually do the manipulations and calculations. Okay. So what is AK? Give me a equation in terms of AK and BK plus P. BK, comma P, sorry. Anybody? It will be better if you speak up.
Like we can probably say AK plus summation BK comma P for P less than K is greater than equal to K.
Exactly. So K minus union of BK comma P.
Wait, how are you doing
P
union?
less. It is union, right? Because we want to
It's a
take every
set or it's
pi.
a thing? Like you defined BKP as a set or as a number?
BK comma P is the
Yeah,
num.
like
Okay, yeah, we can do the summation, but we have to introduce the inequality sign then.
yeah.
Because things will be, yeah. Okay. I can do set also, like, then I have to like write one extra step, but yeah, makes
Yeah,
sense.
like the inclusion exclusion stuff.
Mhm. And one fun thing I'll just
I
tell at
think the
start.
inequality sign should be reversed.
Yeah, true. Hmm. Now you want to count this thing. Also, I want to mention one thing. Should I mention it or not? Okay, I should not. I'll tell at the end.
So we're trying to show that K minus like that summation thing is not bounded, right?
Mhm.
Okay.
So try to show that uh, something with this thing, summation P less than equal to K, BK comma P. uh, try to bound or something like we try to use the fact that n square plus 1 has two solutions for prime. It has two solutions. So can we bound this thing somehow? See, it's not hard. Like if it has two solutions, how can you bound it? How many solutions can it max
2
have?
times
Because
floor of K by P or wait, no, not exactly that.
it has mod p square, so k by p square, right?
Yeah, 2
Yeah.
times floor of K by P square, I believe.
Yes. So you can bound this by k minus 2 times summation. Okay, is the class extend by 10 minutes? Is it okay?
Yeah.
Actually, I only have exams, so that is the issue. I have to leave. But let's see, I'll try to finish this early. K by p square. Okay. Now what can you do? More things with this. Now these are just a little bit of algebra with NTs, so we have to manipulate and things. Also, I want to mention P1 mod 4 gives P greater than equal to 5, right?
Please
Right?
become taller in life. Get a life. No one likes you.
Hello? Okay. So P1 mod 4 gives P greater than equal to 5, right? So that means uh, we can also introduce p greater than equal to 5 here. And you will see you actually need this later. If we also include p2 and 3, this will become bad because the inequality sign will not match. Obviously, you can't see this at first. So at the end, you can notice, but I'm for the constraint of time, I'm introducing this at the first. Then we need that p greater than equal to 5 also. Hmm.
Uh,
Now ideas.
Could you explain like how did floor of k by p square came again?
Yeah, I'll explain that. So Ka should be 0 mod p square, right? So how many primes can divide it? So if it divides, if it is divisible by p square, then k by p square should also be divisible by some other q square. So you divide all those primes. So the number of primes can be at most k by p square. Because if it has more than k by p square things and you do all the products of that, they will like exceed k. So you can't have more things than that. So you can at max have k by p square. So it is floor of k by p square because it's an integer after all. And for every prime, you have two solutions. So you choose a prime, you have two solutions. So your count of counting this. And because for every prime you have two solutions, so total number of solutions will be 2 into summation bk 2 into k by floor of k by p square, and you are doing the summation. So summation p less than equal to k, floor of 2 into floor of k by p square. And you also introduce the fact that p greater than equal to 5 because you need it at the end, and we proved p should be 1 mod 4 to hold this. Like, this is hard to see at first that why did we introduce, but at the end when we do the inequalities, it will become clear that and it's a fun fact. The only reason we like p becoming 1 mod 4 is p greater than equal to 5. Like, we actually don't need any other thing for p1 mod 4. We for p greater than equal to 5, we can do this. This is quite fun that we don't need any other aspect of it. Okay. Now how to count this thing? More inequalities. Okay.
Bound this by, well, that summation is going to be at most a times 2 times pi squared minus 6 minus the first few terms. Pi squared by 6 minus 1 by 4 minus 1 by 9 minus 1 by 16.
We actually don't want to pi square by 6, right? Because we have p squared. So p square is more constructive than pi square by 6. And actually, we need a little more about p square at end if you see. So the pi square by 6 bound will actually not be that much helpful.
Wait, do we need the floor or can we remove that?
Oh, floor can be removed. So I'll just remove it now. Floor is like, if we remove the floor, there will be a +1 sign. So +2. So this will be summation of you see that? Because floor of x is like x by 1, and you have the 2 at the front. So +2 summation. What will be this? So it will be, one thing is summation 5 less than equal to p less than equal to k. And this thing is the number of primes it has, and you have 2. So it will be, wait, I'll just write this plus 2k by p square plus, it should be minus 2 into pi of k. Pi is the number of primes. So we are looking at the number of primes less than equal to k. We don't care about 2 and 3 because they, for large enough things, 2 doesn't matter. So we'll just introduce 2 into pi of k. Makes sense?
Right.
And what is 2k by p square? Okay. So, I'm
why,
just taking k. Yeah. Any issue?
why are we doing 2k by p squared plus 2?
Because we remove the floor thing, right? So floor is like bad to work with. So we remove the floor thing. And that's why this came. The +1 came.
Oh, got it.
Because it's in minus, so float of x is like less than equal to x plus 1, right? So, and this is in minus, so the inequality sign will change and the +1 will come, if you see.
Got it. Thank you.
Yeah. So we're taking k common
Things like
because k is. Yeah, continue.
wait, floor of x is less than equal to x. Wait, I'm confused.
I'm using the fact that float of x is like float of x is less than equal to
I
x.
think you
Yeah.
need to say greater than equal to x minus 1.
Yeah, exactly. Like wait, 1 sec. Yeah, this works, right? Or am I missing
Yeah, okay.
something?
No, I think it makes sense.
So now we're gonna look at what is O of AK. So we are doing the greater than here because all the things are greater than. So whatever O will get, this is greater than. And we just want to prove that this is non-zero. So even if it is something like log of K, we'll be done because for there will be infinitely many solutions.
Sir, I have a question.
Yeah.
What does O stand for?
Okay, I defined like O at the start. So O is kind of the asymptotic growth. So for a polynomial P of x, we have P of x being O of x to the power n. So at infinity, the growth rate of P of x and x to the power n will be same. So we're kind of defining it like that.
Oh,
So,
thank you very much, sir. Thank you.
Okay. I was okay, yes. What will the O of AK?
Wait, why are you introducing O?
To check the density of AKs. Just we want to prove that AK is something like non-zero, right?
First, don't we want to handle the summation of 1 by p square before doing this?
We'll have to handle, but like we want to introduce like have something such that we can understand what do we actually have to prove, like summation of 1 by p square, which bound do we actually have to prove this.
Okay. Like this
So we are
bound we
trying to
know,
understand that. Like we don't know the summation of 1, but like that is constant, we know, but do we know the actual
right?
value? We probably do. But like what value we need to prove is actually easily provable. Like we don't need any previous theory. So you can do it both ways. That doesn't matter. I was doing it just first because first time I solved it, like I did it like this. So both the things will be same if you handle it either ways. Is this part okay?
Yeah.
And see, pi of k is like k by log k, right?
Sure.
So because it's k by log k, And this thing is like O of k, and this thing is like O of k by log k. So if we want to prove, if we just prove that this is greater than equal to 0, we are done. So this will be O of k, O of k, if just this thing is greater than equal to 0. Do you see why that is true?
Yeah.
So we just want to prove that summation of 1 by p square is
It's less than
equal to half. And this is actually not true if you introduce p to be 2 and 3. That's why you needed and you do k very, very large. So from here you do 5 greater than equal to p. And this is very easy to prove why this is true.
Wait,
Do you see
isn't
why
it
this
still
is true?
true with
What?
2 and 3?
Sorry, I did not understand.
Even if you have 2 and 3, doesn't this still hold? Like summation of
This
1 by p
doesn't.
square?
I don't think this does if you have 2 and 3.
Wait, I'll check.
For infinite, like 1 by 4. Does this hold? I don't think so. And we'll actually prove a stronger condition with this. Like we'll prove that the number of things which is like which is square free is actually more than the number of things which is not square free. So this is actually less than 1 by 4. So the constant is actually like greater than equal to half. So we'll also prove that in this way, because summation of 1 by p square 5 less than equal to p is less than equal to 1 by 4. And if we introduce 2,
I
like there
don't
will be
think we
1 by.
need any of that, right? Like we know, can you scroll up a bit?
Yeah.
Like 1 minus 2 summation of 1 by p square is less than, like it's bounded.
We have to prove it
We
is
can,
positive, basically. This thing is positive. Then we are done.
why do we care if it's positive?
Otherwise, O of AK is greater than equal to some negative thing, and it can be like constant, right? Want to prove that it is positive to work
But
with.
like
Otherwise, we are not done.
even if 1 minus 2 by that summation is negative, it's bounded by like it's like greater than equal to minus 1. We can definitely say that. And then at that point, it shouldn't matter.
What?
Wait,
No, we
like
have to prove.
let s equals 1 minus 2 summation of 1 by p square.
Yeah.
We can like trivially say s is greater than equal to minus 1.
Like, I don't know how we can trivially say, but even if it is true,
Then it's order of k minus 2 pi of k minus 1.
no, the k is multiplied. Like, so if this is minus 1, it will just be minus k, minus 2 pi of k, which is
It's
like,
multiplied?
yeah, like we're taking k common, right? So like 2k, so the whole thing is in
Wait, then
common.
there's some mistake. In the last line with order, you wrote something else, I believe.
I don't think
There's
so.
a minus symbol.
Okay, just
Oh,
remove it.
that's why I was confused. Okay.
Oh, okay. Sorry, sir. Okay, now that makes sense, obviously. Yes.
Like if
Anything
there
will
was a
do.
minus sign over there, then as long as it was bounded, it would be true.
Yeah, then we don't care about this. This is constant. Yeah, for sure. So we just have to show this. And this is trivially true because you can also write this as sum of n equals to 5 to infinity 1 by n square. This is less than summation of 1 by p square 5 less than equal to p is less than equal to this, and this is like 1 by n into n minus 1, which is like 1 by 4. Like you can do all the calculation. I'm skipping the calculation. So this is actually less than equal to 1 by 4, because this is less than equal to 1 by 4. So this thing is like greater than equal to half, and so this is actually O of k. So O of AK is O of k, so there will be infinitely many things. O of k, so we are done. You see, right?
Um, I'm sorry, but I didn't get why you have to do the plus 2 um up there.
Because we want to remove the float sign.
But k by p squared would be greater than k. I mean, floor of k by p squared would be greater than k by p squared, right? So then, wouldn't it be enough if we just did 2k by p squared?
True, we don't need to do it at all. Because we're using the other sign. Like we're using like floor of x is less than equal to x. So if we just change it, yeah, we don't need it. Thanks. Because like this is bigger, so subtracting a bigger thing. Okay. You can remove all of this part then. But like even if this occurred, because this is O of k by log k, this wouldn't matter.
Okay.
But was this floor or ceiling here? Did it do the floor or ceiling part correctly?
It doesn't
I mean,
matter.
this,
It's fine.
yeah. Even if we had 2 pi k, it will be like k by log k, which is like less than O of k. So the total thing will be O of k only. And this actually proves that the constant is greater than equal to half O of k here. And because this part is greater than equal to half, so ak is like greater than equal to ak is k by 2. So for large enough stuff, more things will be square free than non-square free. And if you like optimize the bounds, it has actually been proven that the density of n such that n square plus n 1 is square free is actually like 0.8924. I haven't checked it, but I have read it somewhere. So actually, like a lot more things are, you have to prove infinitely many, but like if you see most numbers will actually be square free than not being square free. So the main idea of this problem was to count AK and BK and introduce the number of solution is 2 and introduce the fact and to do the whole algebra from there. So what was 0.894? Yeah, that was the density. Like we wanted to prove this has like positive density basically. AK is a positive density over K. We wanted to prove that if there are infinitely many solutions, the density should be positive. Not should be positive. Like if we show it is positive, then we are done. But the density is actually 0.8924. That's what I'm trying to say. That it's actually like not only positive, it's huge. So most of the things, so if you check like every n, with the probability of 0.8924 things, n square plus 1 will be square free. Okay, I think I'll end the class here. The issue is, I don't know how to end the class. This is, you can do 2 problems for like practice. So this is one problem. And second problem you can do is like 2023 or 24. I don't exactly remember the year. China MOP5. You'll understand the question whenever you like. It's a density problem if you see China MOP5. One is geo, I think, so you'll understand which one is the actual problem.
I just have one question.
Sure.
So like at the end we got O of k plus I think like whatever I think it was 1 minus 2 I mean like that part. Oh wait, is it k times that value or is it?
Yeah, k times. It is k times.
Okay.
Like, see, if you k minus 2k, so just take common k from the whole thing. So it is k times this part. And the 2 pi k we don't need, but yeah, they're different. Like, basically, this is like we don't need. And this is the part we are working upon because it is k times the whole thing.
Oh, okay. Thank you.
Well,